Hello everyone, I'm Vicky from National Taiwan University. This is a joint work with my advisor Michael Tai. In this talk, I will introduce RayTrack, a visible light communication system with dynamic field of view. This feature allows RayTrack to eliminate interference and accommodate mobility, making it a perfect choice for outdoor mobile applications such as vehicular communications. Visible light communication is directional in nature. Choosing a proper receiver field of view for VLC is always difficult, especially for mobile applications. Both wide and narrow field of view have their own drawbacks. A wide field of view can accommodate mobility better. However, since the receiver would aggregate all incoming light into one signal, strong interference such as sunlight or those from other transmitting cars would easily enter the receiver. This degrades the signal-to-noise ratio or even completely saturates the receiver. On the other hand, we can use a narrow field of view to eliminate interference. But in this case, the mobile transmitter would easily move out of the small field of view and often disrupts the communication link. So, is there a solution to the dilemma of choosing between wide and narrow field of view? The answer is yes. To break this dilemma, we present RayTrack, which can perform real-time dynamic field of view adjustment. RayTrack switches between two states, detection and communication states. In detection state, RayTrack uses a wide field of view as its detection field of view, and quickly locates the transmitters. The high-level idea is to find locations with high receive power at communication frequency from the detection field of view. Once the locations of the transmitters are known, RayTrack switches to communication state. It will create a mask to tighten its field of view so not only light from intended transmitters is allowed to enter the receiver. Multiple transmitters can send their signals at the same time. In this case, RayTrack takes turn to only allow signal from one of the transmitters to enter the receiver, and does this in a round-robin and time division manner. With RayTrack, outdoor VLC has improvements in the following three aspects. First, VLC becomes interference-free. The tight field of view repels the interference from ambient light and from other transmitters, allowing higher throughput. Second, as signals from other transmitters are blocked, conceptually, RayTrack creates point-to-point links which guarantee undivided bandwidth, even in dense deployment. Finally, the need for an access control mechanism is removed. This also means that transmission can immediately take place without any additional delay caused by the protocol. Before we dig into RayTrack's design, let's first go through some background knowledge. First, let's take a look at a digital micromirror device, also called DMD. DMD looks like the picture here and is composed of millions of micromirrors, also called pixels. These micromirrors can be quickly switched between on and off states and usually has a tilt angle of 12 degrees. So, if it's set to be on state, it will tilt 12 degrees toward right and vice versa. By setting the DMD pixels to different states, we can steer the incoming light from different parts of the field of view to different directions. Second, let's talk about compressive sensing. Say we want to know a signal vector x with size n by 1. If x is sparse in some basis, then we do not need to measure x one by one. Instead, we can measure the sum of several values in signal x at a time. If we can choose how to measure x wisely with measurement matrix phi, then we measure with m times, which is less than n and less than what is required by Nyquist theorem. This gives us a high compression ratio given by n divided by m. In order to perform compressive sensing, we need to make sure the reconstructed signal x is sparse in some basis. When x is sparse, it means that most values in x is zero valued with a few exceptions. However, in a lot of cases, x itself is not sparse. Instead, we can find a basis psi which transfers x to coefficient alpha, and alpha is sparse. This is called x is sparse in some basis psi. Note that a good psi may differ from signals to signals, and we would like to find a proper psi which has a very sparse alpha for x. Finally, both alpha and x can be estimated by solving an N1 minimization problem. Now let's take a look at Retrace Key Designs. The main problem in RayTrack is to detect the locations of the transmitters. This slide shows the fundamental design of RayTrack, including a couple of lenses, a DMD, and a photodial placed on the light path of on state. The thing in the detection field of view is projected by the imaging lens onto the DMD. Each pixel of the DMD is now mapped to a small portion of the detection field of view. If we can know the pixels where the transmitters are located, we can turn on only these pixels to create a mask, allowing only light from the transmitter to enter the receiver, and discard the signals reflected by other pixels since they are mostly interference. RayTrack uses compressive sensing to obtain pixels corresponding to transmitter locations. To do so, there are 3 challenges. First, how to minimize the detection time with compressive sensing using a high compression ratio. The second challenge is to enhance the reliability of detection performance with high compression ratios. Finally, the third one is to increase the sparsity of the detection field of view. Next, let's take a look at the solutions to these 3 challenges. The first challenge is to minimize the detection time. Why is this necessary? To be able to track a mobile transmitter, as an example, let's assume we have to detect at 10 Hz. With sequential scanning, which measures the pixels one by one, it takes too long to achieve 10 Hz, without even considering the time for communications. With conventional compressive sensing, over half of the time is spent on detection, and this cannot be used for communications. Thus, the goal here is to reduce the detection time or increase the compression ratio to the limit, so that we can save time for actual communications. We can formulate the detection problem as a compressive sensing problem. The detection field of view is the signal X we want to reconstruct. To obtain each entry in Y, we first split the measurement matrix to vectors and reshape them to a 2D dimensional pattern and display it on DMD. This pattern is a binary pattern with value 1 and -1, indicating the pixel state on and off respectively. Those projected onto on pixels would be steered toward the on-state photodial and aggregated into one signal. The light signal projected onto the off pixels would be steered toward an empty space and discarded. In this case, for the on-state photodial, the -1 value in the pattern is 0 out, since it does not receive any signal reflected by these -1 off-state pixels. Accordingly, we can define matrix phi plus and measure the intensity vector y plus. However, discarding light from the off pixels is a waste. To recycle it, we adopt a technique called complementary compressive sensing. To do so, we add an off-state photodial on the light path of off-state pixels. Similarly, for the off-state photodial, the one value in the pattern is 0 out. We call the matrix as phi minus and the measured intensity vector as y minus. With received signal from both photodiols, we can now perform complementary compressive sensing. How do we do that? By subtracting the measured intensity of off-state photodial from that of on-state photodial, we can obtain the original matrix with both 1 and -1 values. Moreover, with the assumption of noise uniformly distributed on DMD, we can mitigate noise terms. Our results show that with the help of complementary compressive sensing, we can increase the compression ratio from 4 to 20. The second challenge is to enhance the reliability of detection. Many existing works randomly select a set of patterns from a 4-measurement matrix. However, with a high compression ratio, we observe that random selection sometimes fails to provide correct results. To address this issue, we want to optimize the selection of measurement matrix. We observe that good detection results tend to be produced by a set of patterns with high measured intensity values. To find these patterns, we propose an algorithm to pre-learn the matrix. First, the training dataset is collected in an outdoor scenario at 45 meters with one transmitter. We collect the measurement intensity for all the patterns in a 4-measurement matrix. Next, we rank the performance of each pattern by sorting its measured intensity as a likelihood to have high values. Finally, the M patterns with the highest likelihood are chosen to construct the pre-learned matrix. The final challenge is to enhance the sparsity of the field of view. In compressive sensing, to have the same level of estimation quality, the number of required measurements grows with the number of non-zero entries. However, the more measurements we perform, the longer time it takes to complete one detection. So let's first see what would increase the non-zero entries. The first one is of course higher number of transmitters. However, this is a given parameter that we have to work with. The second one is the leakage of the transmitter projection to its neighboring pixels. The leakage causes the number of non-zero entries much more than the number of transmitters. For example, for a view with 4 transmitters, we expect the projection on DMD to have only 4 non-zero entries. However, the actual projection is like this, with more than 30 non-zero entries due to the leakage of the projection. To address this issue, we introduce a customized basis to enhance the sparsity of the signal. The intuition is to use a proper basis to capture the projection pattern of the transmitter. In this way, the basis can condense the leakage, bringing the number of non-zero entries closer to the number of transmitters. To customize the basis, we first need to model the projection pattern. We collect the received power distribution of a transmitter from 10 to 45 meters. Next, we use a two-dimensional Gaussian distribution to fit the measured received power pattern and create a discrete Gaussian-like mask. Finally, to generate the Gaussian-based basis, we consider each column of the basis matrix psi a possible location of a transmitter. We convert each of these n columns to a 2D matrix and place the Gaussian mask at different locations, as shown in the animation here for different columns. Then these 2D matrices are converted back to columns and put together to form psi. Now let's talk about our implementation. This figure shows our prototype of RayTrack, including a DMD, 2 photodiodes, and a set of lenses. The imaging lenses used in RayTrack creates a detection field of view covering a lateral distance of 3.7 meters at a longitudinal distance of 20 meters. Therefore, a transmitting car taking right and left turns or making lane changes will be covered by the detection field of view in most of cases. Finally, let's take a look at our evaluation results. Due to the time limit, here we only show part of our results. Please refer to our paper for the others. First, we compare outdoor detection performance with one static transmitter at 30 meters when using different compression ratios. Here in the left plot, we compare the detection performance with random matrix and with prelim matrix, both using dual photodiodes. The x-axis shows the applied compression ratio and corresponding detection time, and the y-axis is the detection rate. We can see that to achieve a detection rate of 100%, prelim matrix is able to reduce the detection time by a factor of 2. Next, we compare the performance of single and dual photodiode configuration when both are using prelim matrix. The left and right photodiode here represent the on and off state photodiode respectively. We can see that to achieve a detection rate of 95%, dual photodiode is able to reduce the detection time by a factor of 3. The plot on this slide shows the detection performance with one transmitter at different distances when using a compression ratio of 20. This compression ratio corresponding to a detection time of 19 milliseconds. From the figure, we can see that the dual photodiode with prelim matrix always outperform the others. In addition, comparing the performance using dual photodiode with random and prelim matrix, the prelim matrix is able to extend the zero missing detection range by 10 meters. We also evaluate our system with a freeway driving experiment including lane changing and turning maneuvers. An LED serving as the transmitter is installed on the leading car, and the RayTrack prototype is on the following car. A LiDAR and a camera are used to obtain ground truth. Let's first take a look at the overall detection performance in the driving evaluation. In this figure, the x-axis is the lateral distance while the y-axis is the longitudinal distance. The following car is assumed to locate at the origin. The box here represents the relative position of the leading car with respect to the following car. As you can see, the system can achieve a detection accuracy of over 90% at 35 meters. In addition, reliable detection can be performed with lateral distance ranging between -1 and 1 meter. Here's a demo video of our real-time detection performance. On the upper left is the detection result. A dark blue block means a correct detection, where a red block means a missed one. We use lighter blue to indicate the historical detection trace. On the bottom left is the leading car's relative position to the following car. As you can see, RayTrack is able to reliably detect the LED on the leading car throughout the lane changing maneuver, even when the leading car is at the adjacent line. In conclusion, in this talk, we introduced RayTrack. To the best of our knowledge, this is the first VLC system with dynamic field of view supporting freeway mobility. RayTrack enables interference-free VLC link without the need of an access control protocol. In addition, RayTrack is able to perform fast and reliable detection in less than 20 milliseconds and with a detection range of up to 35 to 45 meters. Thank you for listening, and I'm glad to take any questions.